Hey, welcome to this video. This will be a crash course on linked lists. So linked lists are a data structure that holds ordered data similar to an array, except with some minor differences, right? And just like an array, well, the ordered data it holds can be anything. In this example, it's numbers, but it can also be strings, arrays, other objects, slash, hash tables, etc. And each of these things that holds a value in our linked list is called a node, right? So this node has 22 in it, this node has 2, you call this a 77 node or a node of 77 in it. And each node in a linked list has two properties, a value property and a next property. So for this node, the value property is set to 22, that's the value that node holds, and the next property points to the next node it points to in the linked list. So this 22 node's next property is the 2 node. The 2 nodes next property is the 77 node, etc., etc. And lastly, in a linked list, you refer to the first node in the linked list as the head node. So, right, this is the first node. And the last node in the linked list is referred to as the tail node. And we know this is the last node in a linked list in our code because this next property points to null or nothing. So we can create a very quick rudimentary linked list in our code, which is exactly what I'll do. So I'll say let first be equal to an object with a val property of Kevin. So in this example, I'm going to represent each node in my linked list as a JavaScript object, right? And each node has to have a value property and a next property. I would just call it val. And now I'll say first.next will be equal to a node where the value is a string of is, and the third node is equal to a node with a value of handsome, right? Let's console.log out our linked list. So I'll say console.log the first node of our linked list. And now, if I run my index.js file with Node.js, this is our linked list. It's 3 nodes, right? First node is Kevin, second node has value of is, third node is handsome. Cool. Now, this is a very rudimentary and basic way to create a linked list, but once our linked list gets really, really large, like say, I don't know, 1 million nodes, well then adding a new node is going to be a pain. And what if we want to insert a new node at the beginning or remove a node from the beginning of this linked list? This basic way of creating a linked list is not going to cut it. So we're going to use a object-oriented programming approach to do that, or something similar to it. So I'll use a class syntax, and I'll say node, and what should our node have? Well, again, remember each node has 2 properties, right? A value property, which I'll just call val, just to save myself some typing, and a next property, and I'll just set it to null when a node is first created. But when a node is first created, I'll set val to be the val passed in. And then I'll have a, let's see, a linked list class. And again, you can create a linked list doing this, but once our linked lists get really large, using this class syntax is going to make the operations we do on our linked list a lot easier. So I'll say class linked list, constructor. And remember before that I said a linked list has a head and a tail property. Head points to the first node in the linked list. Tail property points to the last node in the linked list. So I'll say this dot head is equal to null initially, right? Same with tail. And for our crash course, I'm just going to focus on 2 methods. The first is push, which takes in one argument, a val. And just like array.push, our linked list.push will push a new node to the end of our linked list. So how do you add a new node to the end of our linked list? Well, what we're going to do is, I'll show you in Visual Algo very quickly. So you're going to create a new node, in this case an 80 node, say tail.next, right? Have an arrow point from here to here. Tail.next is equal to the newly created node, and then set the tail property to be, well, the new last node. That's what I'm going to do. So I'll say const new node is equal to new node val, right? We pass in the val from here to down here, and our node takes in a single argument of val. That gets set to here. Now I'll say, or I'll do an edge case if our linked list is empty, then, well, this dot head is equal to new node, and, well, this dot tail is also equal to the newly created node. Otherwise, if our linked list is filled out, I'll say this dot tail dot next is equal to new node, and this dot tail is equal to new node. Our last method for our crash course will be the shift method, which removes a node from the start of the linked list. And how would we go about doing that? So, if we want to remove a node from the start of our linked list. All right, that was pretty fast. Let's rewind a bit. So, our old head was 22. That was the old first node of the linked list. And we'll just set the head to be the node ahead of it. So head will be up to this 2 node, and then our linked list will kind of forget about it. So let's skip forward. Yep. So let's implement shift very quickly. So I'll say if our linked list is empty, then return. Right? There's nothing to remove. We don't have to go through with the rest of our code. Otherwise, let's see. Const old head is equal to this dot head. This dot head is equal to old head dot next. And I'll say return old head, right? Because in JavaScript's array.shift, it returns the value from the array that's removed. I want to simulate the array.shift with our linked list.shift. Okay, and now that we've implemented our linked list using the class syntax, let's see if we can recreate what we have up here with the new class syntax. So I'll say const list is equal to new linked list. Then I'll say list.push Kevin. We want to do Kevin is handsome. So I'll copy this, do it twice. And see how much easier this is to write than, say, all this. Now, of course, we only have 3 values, so like the benefits we see are pretty negligible. But what if our linked list becomes, again, 1,000,000 nodes? If we did it this way, it's going to get old really fast, or rather, very tedious. Right after this linked list syntax, well, it's pretty simple. Let's make sure it works. So I'll say console.log list.head. If I bring up my terminal and run that node index.js file again, Oh, okay, let's remove this console log. I'll just keep this in the video. Okay, so console.log list.head. Run again, and we get, well, a linked list that has 3 nodes in it. Kevin is handsome. Let's make sure our shift also works. So I will console.log out a line just to make our print statements a bit easier to read. Then do list.shift, which again removes the first node in our linked list. And then I'll say, well, console.log list.head. So now our linked list should be is handsome because we removed Kevin. That's the first node on our linked list. So I'll clear this out. Yep, it's now is handsome. We have that line to separate things out. So what is the time complexity for our linked list? So adding to the end is O of 1 or constant time. Why is that? Even if our linked list is 1,000,000 nodes long or 1,000,000,000 nodes long, to add a node at the end of linked list, we just say, hey, tail.next is equal to that newly created node, move the tail property up 1. We don't have to iterate through the whole list. We just have to modify this tail and tail.next property. That's constant time. That's why it's O of 1, and adding to the start is also O of 1 or constant time. Again, even if our linked list is 1,000,000, 1,000,000,000 nodes, to add a node to the start of the linked list, we just change the head property. Now, if linked lists and arrays both hold ordered data, when would we ever choose a linked list over an array? That's a pretty common question. So, The answer is we want to use a single linked list over an array for storing ordered data if you plan on frequently inserting data at the start. So again, I just went over why adding to the start of a linked list is O of 1 or constant time. But for an array, adding to the start of an array for your ordered data is O of n or linear time. As we can see from the big O complexity chart, O of n has fair time complexity, O of 1 is excellent. So linked lists are faster at inserting to the start of the ordered data than an array. So the next question you might be asking yourself is, so why does an array have linear time complexity for adding to the start? That's because, here's an example. Let's say this is our array of students that has 4 things in it. And I want to insert a new student at the start of the array. Let's say Jacob. Once I insert Jacob to the start of this array, all the index values are wrong. They're messed up, right? Jacob should be index 0, not Kevin. So I have to re-index everything, right? I have to change this index, then this index. I have to go over every item in the array and re-index everything. So if our array is a million things, I add to the start, I have to iterate over the rest of the million things in the array, right, to re-index everything. That gives us, well, O of n linear time, whereas with a linked list, we just have to move the head property. So again, that is why you would choose a linked list over an array for storing ordered data. And that should be it for this video.